guys, welcome back. So this is the second lecture on complex numbers. Earlier we covered some basics of complex number, like how to treat the iota sign, what does complex number actually mean, and then taking conjugate and modulus and all. Right. Now this is the second lecture which in which we are going to cover how to geometrically represent complex number in different planes. So the plane in which a complex number is represented is called the Argand plane. It is almost similar to the xy plane that we typically have in the coordinate geometry, right? So typical Argand plane goes like this. So there are two axes, right? And this axis is called the real axis, and this axis is called the complex axis, right? Now any complex number which is z is equal to a plus iota p. In this, let's treat it as a vector which we write like x I cap plus y j cap, right? So this is the unit vector in the x direction, this is the unit vector in the y direction. So likewise, we call this is the imaginary part p, this is the real part a. So it says go to a unit here, which is this length is a, right? So this length is a, and if I go the positive complex axis direction to a point p, so let's go to a point p, right? So this is the distance which is called the p, right? So this point is z is equal to a plus iota b, right? So typically what happens is, now this point, right, the intersection. So we can see just by having this geometric interpretation of a complex number, we are able to solve many questions just by looking into it, right? So now looking some basics of it, if we connect, so this is the origin, right? So this is the origin, okay? So if we connect the origin to the complex number by an arrow, right? So let this be an arrow, right? So what happens is, I know this line is b again, so I know the length of this, so the length of z is nothing but a square plus b square and root, right? So this is nothing but a square plus b square, right? So this is coming from the Pythagoras theorem. So now what we know, what is this number a square plus b square? This is nothing but z bar, right? Root of z bar, right? So this is nothing but the modulus of z, the modulus value of z, right? So the length of z. So what happens is, this is called the z, right? The modulus of z. So when we draw a complex number on an Argand plane, so the distance of the point, the complex number from origin, is the modulus of the complex number. So that is one representation that we can definitely use. Now in this form, we can represent a complex number which is of the curve form z is equal to a minus iota b, which is nothing but the conjugate. This is nothing but z. Suppose I call it z2. So z2 is nothing but z conjugate, right? So if I see it logically, now I have to move to the distance. So if I remove this, right, this distance is a. So if I move in this direction, so this point, this is nothing but z bar, because this distance now is minus b, right? So what I am doing is, I am going a direction, a units in this direction, that is the real axis direction, and minus b in the complex axis direction. So this is the z bar. So z bar is nothing but the image of the complex number in the real axis, right? So if I take the image of this, right, so this is going to be this, right? Now this is a complex number, another one, z1. So I know that z1 bar is going to be like this. So this is going to be z1 bar, right? So this is one representation of complex number in the Argand plane, right? Now taking it forward, there are different ways of looking into it, right? So if I again take this, okay. So if I take this as z is equal to a plus iota b, right? Now if I take this angle as theta, right? So this is a, of course. If I write a is nothing but modulus of z cos of theta, right? And b is nothing but modulus of z sin of theta, right? So this is sin theta, this is the cos theta, this we know from trigonometry. Now now when I write this complex number z, what I can can write is z is equal to modulus of z cos theta plus iota modulus of z sin theta, right? So if I take modulus of z as constant outside, so it becomes modulus of z cos theta plus iota sin theta, right? So it becomes like this, and modulus of z we typically write it as r, right? So the general form is z is equal to r cos theta plus iota sin theta, right? So this is another way of representing a complex number, right? So this is nothing but the polar form. This is nothing but the polar form, right? And the earlier was a simple representation geometrically in the in the argument plane. So these are the two ways in which we can represent the complex number geometrically, right? These are very useful, like when we are doing some problems, then definitely these turn out to be of good help, right? So let's see quickly some examples, and that might make it more clear. So let me quickly take an example. It says represent the complex number z is equal to 1 plus iota root 3 in the polar form, right? So I know the polar form is r cos theta plus iota sine plus iota r sine theta, right? So that is one. So now if I compare these two forms, I know my r cos theta is equal to 1 and r sine theta is equal to root 3. From this I get it, right? Now if I square both the side and add, so I get r square sine square theta plus cos square theta is equal to 3 plus 1 is equal to 4. This I know is nothing but 1. This implies that r square is equal to 4, right? Now when I showed you the diagram, I said this is nothing but modulus of z is nothing but r, right? So this is nothing but the length of the complex number, right? So the modulus is the length, that is the distance of the complex number from origin, right? So it cannot be negative, it has to be positive, right? So this implies that r is equal to 2. We cannot write that r is equal to minus 2, right? So I get the answer that r is equal to 2, so I got the modulus of z. Now putting this value in this equation, it says cos theta is equal to 1 by 2, and this can be solved, right? So this is nothing but the trigonometric equation. Okay. So that is the general solution. So that is it, right? So okay. So this gives like theta is equal to pi by 3. Okay. So that's fine. Okay. So now my complex number is 2 cos pi by 3 plus iota sine pi by 3, right? So that's the way it is. A very simple question. Taking another example. Convert the complex number minus 16 upon 1 plus iota root 3 into its polar form. Now I know that whenever I get a complex number, the denominator in division form, I have to multiply it by its conjugate. So I do it very quickly. I get 1 minus iota root 3. This is when I multiply, I get a square plus b square. So this is nothing but this negative become positive, so it becomes 16 root 3 iota minus 16 upon, this becomes a square plus b square, that is nothing but 4, right? So that becomes 4. So it becomes minus 4, I can put it here, plus 4 root 3 iota, right? So I just cancel this 4 from there. Now this is nothing but r cos theta and plus iota r sin theta, right? So I do it again, r cos theta is equal to 4 and r sin theta is equal to 4 root 3, right? Now I square and add, so I get r square cos square theta plus sin square theta becomes 1 is 16 plus 16 into 3 is equal to 48 plus 16 is 64, right? So r square is equal to 64, then again r is equal to 8. This implies that cos theta is equal to 1 by 2, right? So the moment I get cos theta is equal to 1 by 2, I get theta is equal to 2 pi by 3, right? So here this is r sin theta is r cos theta is equal to minus 4. So here it becomes it becomes minus 1 by 2, right? So it becomes minus 1 by 2. So this this implies that theta is equal to 2 pi by 3, right? And that's the answer, right? So we get r is 8. So 8 cos 2 pi by 3 plus iota sine 2 pi by 3, right? So that's the answer. That's the representation. So okay, so that is again a straightforward question. Now this complex numbers, where do they arise? So one way of finding complex number is like when we are solving the quadratic equations, right? So whenever we are finding the the root of a quadratic equation, we know the Sridharacharan method, like ax square plus bx plus c is equal to 0. So that is one equation that we want to solve, and I know that the answer for this is x is equal to minus b plus minus under root of b square minus 4ac upon 2a. So that's the equation that I know, right? The issue is when we studied those, we said like b square minus 4ac has to be greater than or equal to 0, right? Then only it's solvable. But now what happens if this b square minus 4ac is less than 0, right? So it is a negative, right? So what happens is when this quantity is negative, so we are taking the root of negative, but still now we know that how to solve it. We are going to get iota terms, right? So the root is going to be a complex number, and this is one way that roots are going to be generated. Like those are the roots of the quadratic equation. One thing to notice here, like I know the sum of root is minus b upon a. So the root 1 plus root 2 is equal to minus b upon a, right? Now this is a real number, right? So how come a sum of two complex numbers, that is, say suppose we get two roots, right? So there are root 1 and root 2, right? Definitely one is complex, right? Other is let's say anything. So I know this, if it is a complex, let me represent it as a plus iota b, right? So I say a plus iota b times this plus r2 is something real, right? This something is real, right? So now if something is real, then there are only two possibilities, that either this thing is 0, but if this thing is 0, then I bring my assumption, like the basic condition is not fulfilled. So this cannot be 0, that means there has to be some part in it, imaginary part, that has to cancel it. So this is nothing but something a1 minus iota b, right? This has to be in the form of a1 into minus iota b, right? So typically what happens is, I get like these have to cancel, so these cancel out, and then we get is like a plus a1, and generally what happens is a is equal to a1, right? So we get a complex conjugate. So the roots, if they are imaginary, so we get in the form of, so this one is a plus iota b, this has to be a minus iota b. There is no other possibility left, right? So that's one good way to check, like if we are getting good results. So okay, so this is one. Now theory wise we have covered everything, like on what the questions can be formed, we have covered all the points. Now what we can do is we can typically quickly take few good examples, like and then I think we're done. So let's take the first example and then keep solving it from the start. So it says find the conjugate. We have to find conjugate of 3 minus 2i, right, times 2 plus 3i upon, right, 1 plus 2i times 2 minus I, right? So this is something that we need to solve. There is nothing that we can do typically. We simply have to multiply. So let's multiply this. 3 and 2 becomes 6. 3 and 3 becomes 9i, right? 2 and 2 becomes minus 4i, and 3 and 2 is 3 and 2 is 6, and minus 1. So this is nothing but 6, right? So this is 3 and 2 is negative. Negative I square is minus 1, so it becomes plus 6. Likewise, we solve this. It becomes 1 plus 1 into 2. 1 2 becomes 2 minus iota. This and this becomes plus 4 iota, and this becomes minus 2i square, that becomes 2, right? So it becomes 12 plus 5i upon 4 plus 3i, right? So we got it in the standard form. Now we know what needs to be done. Simply needs to multiply by a conjugate here. 4 minus 3i upon 4 minus 3i. Conjugate becomes a square plus b square. So I know the denominator becomes 16 plus 9. And the numerator becomes simple multiplication. So 12 and 4 becomes 48. 12 and 3 becomes 36. 5 and 4 becomes 20. 5 and 3 becomes plus 15, right? This becomes plus 15, okay? So this becomes 25. 48 plus 15 is 63. 63. Then becomes 69 upon 25, right? So now the complex conjugate is nothing but the conjugate of this is equal to 63 plus 69 upon 25, right? That's the answer. Okay, so that's a pretty straightforward question. Nothing much to be done here. Now, let's take another example quickly. So it says, the question says, find the modulus and argument of the complex number. So we have to find the modulus and the argument. So 1 plus iota upon 1 minus iota, right? So for the modulus, again we know something that we have to do is like, multiply by 1 plus iota and 1 plus iota. It becomes a square plus b square, that is nothing but 2, 1 plus 1 square plus 1 square. And that becomes 1 plus I whole square, that is nothing but 1. A square plus b square is minus 1 plus 2ab is 2 iota, and this becomes iota, right? So the modulus is nothing but this is square, that is equal to 1. So modulus becomes 1, and the argument is the value of theta. So let's represent it in the polar form. I can clearly see this is nothing but this point. So the angle has to be nothing but pi by 2. So the argument is pi by 2 and r is 1. So this becomes r cos pi by 2 plus iota sine pi by 2, right? So this is the argument and this is the modulus, right? So that's a simple question that was required to be solved. Okay. Now let's take another example quickly. So the example says if x plus iota y is equal to a plus iota b upon a minus iota b. So right, so they are giving it as like this, and they want to prove that x square plus y square is equal to 1. This needs to be proved. Okay. So now, few things that we can do is, when I see this in denominator, I simply have to do one thing. I simply have to multiply, so that becomes a plus iota b whole square upon a square plus b square. I am doing nothing but I am simply multiplying it by the complex conjugate of this, that is multiplying by a plus iota b from both sides, and the denominator becomes a square plus b square. So this becomes a square minus b square plus 2ab iota upon a square plus b square upon a square plus b square, right? So this is nothing but is equal to x plus iota y. This implies that x is equal to a square minus b square upon a square plus b square, and y is equal to 2ab upon a square plus b square, right? Now when I solve for x square plus y square, what I get is a square minus b square whole square plus 2ab whole square upon a square plus b square whole square, right? So when I see this, I solve this, I get a square square plus b square square minus 2 a square b square, and this becomes plus 4 a square b square, right? So this cancels out, and this becomes plus 2, and this is nothing but a square plus b square whole square, right? A square plus b square whole square, that is the numerator and denominator is same, so this divided by a square plus b square whole square, this is nothing but equal to 1. So whenever I have this thing, I know that okay, x square plus y square has to be 1. So when a complex number is represented in the form of so it says, what does it mean rightly? If z1 is equal to z2 upon z2 bar, right? If z1, a complex number, is in the form of a complex number divided by its conjugate, this implies that modulus of z1 is nothing but 1. So that's the modulus of that complex number, that is 1, right? So a division of two complex number, wherein one is the conjugate of other, the modulus of that is always going to be 1, right? So That's a good way to see, like So, by the way, in the last question, if we see the trajectory, so this is the circle, right? So that's a circle in which this is going to be 1. So on this, every point is a ratio of two complex number where we are the complex conjugate, right? So this is nothing but cos theta plus iota sin theta upon cos theta minus iota sin theta, right? In that way. That's the ratio of two complex conjugate, and the value of this is nothing but equal to 1, right? So that's a good way to see. Okay, now taking another example. So they are saying 3 plus 2i sin theta upon 1 minus 2i sin theta, right? So what they are saying is this is purely real. So that means the imaginary part of this complex number is 0. So that's another good way of forming trigonometric equations. So what we have done is we have earlier solved trigonometric equations. Complex number many times give rise to a trigonometric equation, right? So they are saying that the imaginary part is 0. That means they are saying it's completely real. It's a real number. So what happens is if I multiply it by the complex conjugate, right? 1 plus 2i sin theta and 1 plus 2i sin theta, right? So it becomes, the denominator becomes 1 plus 4 sin square theta, right? A square plus b square, and this becomes 3 plus 6i sin theta plus 2i sin theta, and this becomes 4 sin square theta with the negative sign minus 4 sin square theta, right? So this is the imaginary part, right? This is the imaginary part, and that they are saying is 0. Now I don't care about the denominator, by the way, because this is 0, then it does not matter, right? So the numerator has to be 0. This implies that 8i sin theta is 0. This is a constant. This implies that sin theta is equal to 0. This implies that theta is equal to n pi, right? So for all the numbers, this will satisfy, when they fall in this. So any angle here or here, here or here, here. So all these points, this equality is going to be satisfied, right? So this is nothing but using complex number we got the trigonometric equation and then we solved it to get the answer, right? So we know how to solve trigonometric equation. I have already told you in the chapter of trigonometry, how this can be solved. So it says z is equal to I minus 1 upon cos pi by 3 plus iota sine pi by 3. So that is a complex number that's given and we have to write it in the polar form. Now I know cos pi by 3 is nothing but 1 by 2 and this is root 3 by 2. So I simply do it in this way, iota minus 1 upon 1 by 2 plus root 3 by 2 iota, right? Whenever I have in denominator, I know that I have to multiply by the complex conjugate. It becomes I minus 1 times 1 by 2 plus root 3 by 2 iota upon, when I multiply it becomes a square plus b square is equal to 1 by 4 plus 3 by 4, right? So when I multiply this again, this becomes 1, by the way, right? This becomes 1, so it is gone. So this is nothing but I by 2, right? First terms, and then it becomes minus root 3 by 2 iota is minus 1 square, right? Minus 1 by 2, this becomes this, minus 1 by 2, and then this becomes minus root 3 by 2 iota, right? Okay, so it becomes minus root 3 plus 1 by 2 plus 1 minus root 3 by 2 iota, right? So this becomes like this. So when we solve the trigonometric equation, so we know that this is nothing but this is equal to theta is equal to 5 pi by 12, right? So in this equal to theta is equal to 5 pi by 12, right? Okay. So perhaps this is the last example, guys, on complex numbers, and these are the typical questions that we are going to get in the chapter of complex numbers. Hope you like this video. Thanks for watching, and we will cover the next chapter in the next video. Thank you.